All right, guys. So now we're moving into the next chapter, stoichiometry. Very large word and very somewhat complex material. You are going to be getting a help sheet attached to the slideshow that you may want to print out or save or anything like that, because it's actually going to be very beneficial for you to use as you're going through these conversions. Okay, so the very first conversion we're going to use is incredibly easy, so there won't be a whole lot of steps to that one. But as you move along and we start talking about more stuff, there's going to be a lot more steps. So that conversion sheet will actually be very helpful for you. Okay, so let's get started. First of all, stoichiometry is one of the essential pieces of chemistry. We use it all the time in regular chemistry, in terms of lifestyle, different things like that. You actually can probably use some of that when you're talking about dimension analysis and things like that and trying to figure out complex problems. Okay. So let's start off with our notes and filling in our notes, okay? So the methods of stoichiometry. So we can measure amounts of substances involved in chemical reactions and relate them to one another. So we're actually going to take the last two chapters and kind of combine them together. So we're going to take the chemical reactions chapter and use that knowledge that we have from there and the mole chapter to do some calculations with stoichiometric calculations. So for example, a sample's mass or volume can be converted to a count of the number of its particles, such as atoms, ions, or molecules, okay? Remember, when it's written in red, that's what you're going to copy down. So the group or unit of measure used to count numbers of atoms, molecules, or formula units of substances is the mole, okay? And it is abbreviated MOL as to not get confused with the animal mole, okay? Now, here are mole ratio, how are mole ratios used in chemical calculations? Okay, so mole ratios are used to convert between moles of reactant and moles of product. Okay, a mole ratio is a conversion factor derived from the coefficients of a balanced chemical equation interpreted in terms of moles. Okay, now just looking at this, you notice how big the numbers are. Okay. And the reason I'm doing that is because I'm trying to emphasize coefficients are how we're going to use, or what we're going to use to do the mole ratio. So I have 1 mole of nitrogen that reacts with 3 moles of hydrogen to produce 2 moles of ammonia. Okay. These numbers are important because this is what we're going to be using in order to determine how many moles of a reactant we need to produce so many moles of a product, or how many moles of one reactant do we need to react with so many moles of another reactant to produce products. So you can interchange them. It doesn't have to be a reactant into a product. It could be a product to a reactant, and it could be two reactants that we're solving for. Okay. All right. So steps for converting between moles of one substance and moles of another substance. The very first thing is you're going to write the balanced equation. Now, for the first time that you guys do these calculations, we're actually going to have the balanced equation written for you so that it makes the conversions a little bit easier. Step 2 is determine the mole ratio from the coefficients in the balanced chemical equation, and then solve for the unknown using this ratio. Okay, so let's do some example problems so you can see what's happening here. So the first question says, how many moles of ammonia are produced when you start with 0.6 moles of nitrogen and then it reacts with hydrogen? Now, a lot of times in these problems, they are throwing in extra information to confuse you. So in this problem, you need to focus on two things. How many moles, that's what you're looking for, and you have 0.6 moles of nitrogen. The only purpose hydrogen has in this reaction right now is to tell you that it reacts with hydrogen, right? So that you have the balanced equation. But you're not going to do anything in this problem with hydrogen because it's not really asking you to find anything. But you need to know that in order to know what the balanced equation is. Okay, so let's do an example problem. So you're going to start your problem out, and I'm going to have to move this real fast. So hang on. Figure out how I can move this down. There we go. Okay, I'm gonna move that to the bottom so it doesn't interfere with what we're doing. I set up the balanced equation here. You have nitrogen reacting with hydrogen to produce ammonia. The balanced equation is the most important part because this is how you determine the mole ratio. Okay. Now, It's kind of the same thing. So I always tell people when we're doing these types of problems, you want to identify what you're missing, your unknown, and what you're given. So in this problem, we were given 0.6 moles of nitrogen. So I would write underneath the equation, I would write 0.6 moles. Oops, sorry, didn't mean to do that. Go back. Sorry, guys. 0.6 moles of nitrogen right here. And then I'm looking for ammonia, right? Number of moles of ammonia. So I would put an X underneath that. All right. Because I know what I'm looking at. It's what you don't know over what you do know. Remember, don't overdo. Okay. So back to dimension analysis. So I'm going to start my problem out with 0.6 moles of my N2. And I'm going to multiply that by my mole ratio. How do I figure out the mole ratio? It's always the X over the given in the balanced equation. It's what I don't know over what I do know. So I don't know ammonia. So I'm going to put 2 moles of NH3 on top. And I do know the number of moles of nitrogen. So that's what goes on the bottom. So now I'm going to take this 0.6 and I'm going to multiply it by the fraction to get 1.2 moles of ammonia. Okay. All right, so let's try another example. Now we have a reaction between aluminum reacting with oxygen to form aluminum oxide. So part A says how many moles of oxygen, so that's what I'm looking for, that's going to be my X, are required to react completely with 14.8 moles of aluminum. Okay, so let's see how to do that. So in that problem, you're going to take what you're given. So I would write underneath 14.8 moles of aluminum, and I would write an X over, and I think I just, hang on. I think I just did that wrong. We're just going to solve it for oxygen. So 14.8 moles of aluminum, and oxygen's going to be our X. So we're going to say 14.8 moles times 3 over 4, and it's going to give me 11.1 moles of O2. And the second problem, I'm going to start out with 0.78 moles of oxygen, and I'm looking for aluminum oxide in part B. Okay, so I'm going to make that my X, and I have 2 moles of aluminum oxide over 3 moles of oxygen. So I'm going to take 0.78 times 2 over 3 to get 0.052 moles. So these are how you do the mole ratio problems. Now, following this video, you're going to have an assignment where you're going to be working on the mole ratio. And then on Thursday, you're going to do a POGIL. Remember, those are the process-oriented guided inquiry activities. So you're going to be working on that, okay, to solve various problems. And then Friday, you'll have a quiz. Okay, so if you have any questions, please feel free to email us and let us know, okay? And we will do our best to help you out.